fluorines. And that's because if I imagine changing this material to change the LUMO drop, it's very difficult to only change the LUMO drop without changing the morphology. And we've heard the morphology is very important. So it's difficult to have a control experiment where we're really only changing the energy. Polyfluorines, on the other hand, are fairly disordered, and so this is a way, if you stay within the polyfluorine family, to change the energy of the LUMO without messing too much with the morphology. At least this was the philosophy of this experiment. And so you take this TFMO, blend it with PCBM, you have a massive drop in the LUMO, 1.5 eV, and then you take the PFO, polyfluorine, polyoctofluorine, and then the drop is only just about an EV. Still, an EV is enormous. KT is 25 millivolts. This is a huge driving force. And then you look at the external quantum efficiency when you make the cells, and the one with the TFMO, you actually get measurable numbers. The one with the PFO, when the drop is 29 eV, you essentially get nothing. And so this tells you that just the energy, 1 EV is a large number, just the energy probably is not enough to tell you whether you have sufficient conditions to split the exciton on the interface. And maybe one way to think about this is if you think as a physicist just as energy levels, you're maybe missing part of the picture. This is a very nice review by Jean-Luc Verdas, and he looks at it more as electronic states. So this is your polymer, it gets excited, and then you form these charge transfer states at the interface between the donor and acceptor. And you should think of this maybe as a molecular species, but in the simplest case, in the sort of the ground state, you have the hole in the hole of the donor and the electron in the LUMO of the acceptor. And you can think of that sort of almost like a salt, like a molecule. And it has a ground state, and it has several excited states. And the theory is that the excitation then drops into one of the excited states of this charge transfer complex. And then from there, you get the split charge. And when I say from there, there's a whole lot of other processes that occur when you go from the charge, what people call the charge transfer state, to the charge separated state, and you may have a ladder of states, activated processes. This can become, as I said earlier, as complicated as you want. You can break it up into as many sub-processes as you want, and then in the end, you get your separated charges. So how do you reconcile these two pictures? You can see there's a lot more information in this diagram than in this picture, but in the end, the final energy is what you get when you have your hole in the donor and the electron in the acceptor, and they're far away, and that's the energy that is shown in this diagram here is E final, and so this is what is shown in this electronic state diagram here. And then the drop from the LUMO of the donor to the LUMO of the acceptor is essentially this process from the singlet here into the charge transfer state. That's the sort of elemental process there. And how should you think of charge transfer and charge separated state? So a charge transfer state maybe is a state where the hole and the electron are just across the interface. They're still coulombically attracted to each other. The electron in the acceptor can still polarize the donor. The hole in the donor can still polarize the acceptor. A lot of complicated interactions here, and also an asymmetry given by this interface. In the charge separated state, you imagine it as the one where the two charges are far enough away that their Coulombic interaction has vanished, and now they can move to the respective electrode. This is a cartoon. There is a lot of complexity in this interface. Again, this is a nice paper that shows this. This is a calculation, TCNQ, TTF, a classic donor acceptor of, I guess the 80s this was heavily studied in forms of salt. But the idea is that at that interface, you have a dipole that forms, and if there's a charge transfer, you understand right away when that dipole forms, you have two charges that are separated across the interface. And so this is a total dipole that's calculated as a function of intermolecular distance. The interesting thing is that you can subtract the contribution to that dipole that's due to the charge transfer, and it's these triangles here. And you see that after you're 5 angstroms away, essentially the charge transfer doesn't contribute to the dipole anymore, and you're still left with the dipole moment. And so this tells you that the dipole moment at the interface depends very heavily on the geometry. And so when you make these blends, there is a whole lot of different geometries that occur at the donor-acceptor interface. And so you get a whole lot of different local dipole moments. And as you know, the dipole moments will shift the positions of the HOMO and the LUMO. And so locally, your HOMO and LUMO may be very different from what I measured here when I took my materials separately and I measured HOMO and LUMO and then put them together in sort of an artificial heterojunction. In a real heterojunction, these levels may be shifted by hundreds of millivolts. And so the HOMO and the LUMO of the isolated materials may not always be good predictors of what happens in the charge splitting process, because locally, which is where the charge splitting occurs, the situation may be very different. So this is where the collaboration with Jean Frichet starts, and essentially what happens, to give you a genesis of this collaboration, is they observed a certain number of results that I will summarize here, and they didn't really know how to explain them, and then at a meeting, the students talked to my students, and we had an experimental technique that we thought could help them understand what was going on, and so this is how this collaboration developed. So I will show a few slides from the Frichet group. I don't want to take credit from them at all, but I need to show them for you to kind of understand the story here. So the idea here is to take P3HT and POPT. They look very similar, and the Frichet group is a synthetic group, so they have pretty good control over the materials they make, and so they make POPT and P3HT with similar molecular weight, similar polydispersity, similar region regularity, and all mobilities measured both, in this case, this is in a space charge limited current diode, but also in transistors, they got fairly similar mobilities. When you look at the absorption spectrum, it's pretty similar. There is a major difference, though, is that the maximum extinction of POPT is about a factor of 2 smaller than that of P3HT. So the idea here is, let's take two materials that are different in a few ways, maybe only one, we will know that, but similar in many other ways, and let's see what we get when we make solar cells, if we can extract some trend. So these are the solar cells that we chose to make. P3HT, POPT was the donor, and as an acceptor, rather than using fullerenes, they used CIMOPV. And the idea for them was, well, we can make an old polymer solar cell, and the absorption of the CIMOPV actually complements very nicely the absorption of POPT and recover the solar spectrum better than if we use PCBA. So this is the general. Now the science experiment, because you don't want to mess with morphologies and controlling all that, but sort of the simplest science experiment is to make a bilayer solar cell. So this is what it looks like: glass, ITO, P dot, donor, acceptor, and then the top electrode. And once they do this, they noticed in a reproducible number of times that the current in the POPT cell was always higher than the current in the P3HT cell. And this difference was non-negligible. It was kind of a factor of 2, I'd say the largest difference, but for sure always a reproducible difference. And the VOC was about the same. The major difference was actually the short circuit current. And so this is completely unexpected, because the POPT should absorb less than the P3HT. And so you should get less current. Another thing to notice, actually, this is a surprisingly good bilayer cell. 2% for a bilayer cell is a good result. And this is a publication where this is described. And so now when you look at the energetics of that interface, the HOMO-LUMO picture cannot explain the better performance of the POPT CIMOPV cell. So this is the HOMO-LUMO diagram, POPT CIMOPV. And if you calculate just the drop of the LUMO from the POPT to the CIMOPV, actually you get 0. I think these are measured electrochemically, not positive. With the P3HT, on the other hand, you get a drop of 0.4 eV. So the P3HT has a larger driving force. If I just look at the HOMO-LUMO diagrams to split the exciton with the POPT, the P3HT has a higher absorption, a higher extinction coefficient, and yet the current is larger in the POPT cell. Now, you know that just looking at the difference in LUMO is a little bit of a naive way of figuring out the driving force for charge separation, because you have to remember that the electron and the hole have a Coulombic attraction. There is also the lattice polarization energy, and so the idea was, well, maybe this pendant phenol group does something to the Coulombic attraction, the lattice polarization, does something that I cannot summarize just in a HOMO-LUMO diagram of the unique polymers. And so what that something was a little bit of a mystery, and so this is where we come into play. The interesting thing here that stuck in my mind, being a newcomer, is that you have a strong effect of the molecular structure of what, to me, would look as a sort of a subtle change in molecular structure actually has a pretty large effect on the efficiency of the cell. Now, we talked about the charge transfer complexes. How should you imagine them? Well, it's a CIMOPV molecule with an electron on it, and a POPT molecule with a hole on it, and they're sitting next to each other in a certain geometry. And this complex, and then how it splits, is essentially what drives the charge separation. There's a lot of information. And so this is the complex here in this electronic state diagram. And so the idea is, can you probe what is the energy of that complex? And so you can imagine now exciting an electron from here across the heterointerface and measure, for example, that energy. That sounds simple in principle, but remember that this excitation can only occur where there's an interface. And even though you make a bulk heterojunction cell and you say there's a lot of interface per unit volume, still, per unit volume, there's a lot of interface compared to a flat cell. But compared to the volume density of everything else, there is still a pretty low volumetric density of donor-acceptor interface in your film. So the experimental problem here was I'd like to measure this energy because I'd like to know where does this charge transfer state lie, because then this is what will maybe have to dissociate into charge-separated states in an activated process. So I want to know where that energy is, and how it depends on the molecule that I use. But it's difficult to measure because I don't have, imagine this as sort of a dilute impurity in your film, because it only exists at the donor-acceptor interface. And on top of that, it has been shown that these have typically small oscillator strengths, and they don't absorb that much. So this is experimentally a challenging problem, and this is where our collaboration really started, because it turned out we were putting together a technique, I shouldn't say developing, because this was a well-known technique in the 80s for amorphous silicon, and it's a way to measure optical absorption very sensitively. The way it works is if you think of an optical absorption measurement, if you have a film that doesn't absorb much, you have light that goes through, most of it goes through, and a little bit gets absorbed, and then you compare that to a blank substrate. And so if your film doesn't absorb much, it's sort of like weighing the ship and the captain, weighing the ship, and then by subtraction getting the weight of the captain. So not very sensitive. And this technique, on the other hand, you actually weigh directly the captain. The way it works is that you excite your film with monochromated light, and the film sits in a liquid that changes its refractive index very steeply with temperature. So if the film absorbs, it will heat up, it transfers that heat to the liquid, the liquid changes its refractive index, I come in with a laser, by mirage effect, the laser gets deflected. If I chop my excitation and I lock into the deflection at the same frequency, I can actually measure that very, very sensitively. This was used to measure gap states in amorphous silicon in the 80s. And so we put this together. This is an example of a measurement of a neat P3HT film. And the thing you should pay attention here is the fact that this is a log scale. So you see I can measure absorption over several orders of magnitude, down to, actually we've been able to measure an absorption coefficient of 2 inverse centimeters in a 50 nanometer P3HT film, so that's 10 parts per million. So we can measure absorption down to 10 parts per million. Granted, it takes a week, but we can do that. And so you see a tail, and then you see deep traps, and then these are vibronic peaks. The bottom line is that this works very well. We can measure what happens in a band gap of a material very, very sensitively. If I were to measure the same P3HT film by UV vis, I'd probably be stuck just around here. Actually, you can see it here. It's where this black line stops. This is where our UV vis stops. So we gain 2 to 3 orders of magnitude over standard UV vis. So how do we use this? Well, if you start making your blends, first you want to measure the neat materials. So for example, this is P3HT, which I just showed you a sample selection. This is a CIMOPV. Just neat polymers, nothing special here. If I measure this by UV vis, this is my sensitivity, see how many orders of magnitude I gain, so I can really look in the gap, what happens here. And if I can excite this charge transfer state, I should be able to see this absorption here. And this is a sub-gap feature, a sub-gap compared to POPT and to CIMOPV, right? This distance is smaller than both this one and that one. And sure enough, when we blend them, we see this feature here that is sub-gap compared to the P3HT and to the CIMOPV. And so this, we contend, this is our charge transfer, ground state charge transfer absorption. And then we repeat the experiment with POPT. This is neat POPT. We blend it with CIMOPV, and this is what we get. And you notice right away there's two humps here, so that's kind of interesting. For the P3HT, there's only one hump. And so you fit these humps. The first one was a Gaussian, second one was a Gaussian. They're centered at 1.2 and 1.5 eV. And if you do it with P3HT, it's centered at 1.1 eV. So you see the POPT has two charge transfer states, and in energy they straddle the P3HT. One is lower, one is higher. So first of all, why do you have two charge transfer states? And this is where Jean-Luc Bredas came to help. And what he observed, or what he sort of came up with is, well, with POPT you have this phenyl group that can rotate. So you have essentially two geometries, one where it's planar and one where it's perpendicular. And when you do calculations, you see no matter how you optimize this, how many of these you put together to do your calculation, you see fairly conclusively that the Gemini pair, so the charge transfer state for the POPT perpendicular, is always at higher energy than P3HT and the POPT planar. So the POPT has two geometries, one is higher energy, one is lower energy, and the P3HT is exactly in between these two. So how do we interpret our photothermal deflection spectra? Well, the POPT has two charge transfer states. This is the one where it's planar, this is the one where it's perpendicular, and the P3HT is in between. Well, that's nice, but why does it matter? Well, remember that when you split your charge transfer, this is probably an activated process. And so if my charge transfer state has a higher energy, then the energy barrier that I have to reach to become a separated charge is smaller. Or think of it this way, if my charge transfer state is less stable, then it's easier to break it up into isolated charges. And so this gives me a higher current. And if you think about it, the charge transfer state has sort of a weird job here. On one hand, it has to exist so that, because this is the first step towards charge separation, so it has to have a certain stability in order to exist. But if it's too stable, then it will decay, the two charges will recombine across the interface before they split. And so it has to have this kind of balance between existing but being easy to split. And so what happens with the POPT perpendicular is that it's slightly less stable than its charge transfer of P3HT, and so it can split more easily, and so you get a higher current, or at least that's what that's our theory. And so this is, again, in a diagram of reaction coordinates, the charge transfer state forms. And then if the charge transfer state has a higher energy, it's easier for it to split into donor and acceptor. Now, I actually like this picture, which tends to show why is it that it's less stable. Well, the POPT, because of the perpendicular one, because of this perpendicular rotation, actually it will make the hole sit slightly further away from the electron assigned of PPV. So what this does, it actually reduces the Coulombic attraction between the hole and the electron, so that makes it easier to split that charge transfer state. So the twisted phenyl ring imparts a larger donor-acceptor distance, and that's well known. If you do X-ray on the POPT, you'll see that the pi-pi stacking distance in POPT is about 5 angstrom, while it's about 3.8 in P3HT. So the P3HT packs more tightly than the POPT, and that's because of this twisting of the phenyl ring. And so this leads to a raised energy of the Gemini pair, and that's why it's easier to break it up. But the interesting thing to me here is that you can use molecular design. In this case, it's really structure, and not so much where is the HOMO, where is the LUMO, to increase the photocurrent. You're sort of using a different type of design criteria, not just energetic, but also trying to figure out how to destabilize the charge transfer complex. So this was the story on our work in trying to improve the efficiency of organic photovoltaics by looking at these charge transfer states. The second part of the talk, which is somewhat unrelated, is how do you actually make these multi-junction, multi-layer solar cells? Because if you want to reach, let's say, 15–18% efficiency with single junction, that's going to be difficult. And in the end, one of your competitors is Telluride, so you want to be sort of in that range. So what Peter Clements has proposed, I don't think he was the first one to propose it, but he's really trying to develop this, is what you would call an unconstrained cell architecture. Let's see if I have it in this one. So the idea is as follows. So I can make a multi-junction cell, and you know multi-junction cells from regular 3-5 photovoltaics. You stack them all up, the current goes through the whole stack. So there is a current matching requirement there. All the cells have to be able to carry the same current. Otherwise, you're limited by the cell that performs the worst, because that will be the bottleneck for the current to go out. And in fact, the other cells are just dumping current to the cell that performs the worst. And in 3.5, that's really determined by the fact that you can make transparent electrodes to carry the current through, but you cannot make them conductive enough to carry the current away laterally. If you could, if you were able to carry the current away laterally, then in each cell, you could put a terminal to get the current out, and you would get the current out from each terminal independently, so you don't have that current matching requirement anymore. And in that case, actually, the efficiencies essentially add up. So each subcell has a certain efficiency, you just add them all up. And so in a regular multi-junction architecture, there is no advantage to use a crappy cell somewhere in there, because a crappy cell brings everything down. In this type of multi-junction, what Peter calls an unconstrained cell architecture, there is an advantage to have something that has a lower efficiency, because it adds up. There's always an advantage. You have to balance that out against the cost and the complexity of doing that. But from the efficiency standpoint, there is always an advantage to adding stages. And so this is an example of a real cell. This was sort of a demonstration. This is fairly old. Peter has much better data now. Copper, calcine, C60, and you see there's two cells, so they're both semi-transparent, and the currents, the two cells perform and produce a current. Not particularly good, but you can see that they're independent. You can pick out the current from each cell independently. Now this probably leads to some complexity when you build a module, but we're not thinking about that right now. Right now the advantage here is that you can get higher efficiencies by adding stages. So the key here is to be able to have something that's transparent and conductive enough in the plane, with a large enough sheet conductivity to get the charge away in the plane of the device. And also remember that we want to replace ITO. And so in my group we've been developing zinc oxide as a replacement for ITO, highly doped zinc oxide. But remember, we're depositing this on organic, so you can't really do magnetron sputtering. You can't do PLD, that's too expensive. So we want to have some kind of solution processed zinc oxide that has a high conductivity. Zinc oxide is nice because it's well known. It can be doped with aluminum and gallium. You can actually get pretty nice conductivities. It turns out that most of the high conductivities you get when your substrate is heated, so you've got to go to 300 degrees. We don't want to do that. So our approach is, when we make zinc oxide nanowires that are doped, and then we sprinkle them on the surface and use that as a transparent conductor. First thing you have to try to estimate is whether you ever get to an interesting number in terms of sheet resistance. The figure of merit for a transparent conductor is conductivity divided by absorption over the visible spectrum. ITO, so the higher this number, the better the transparent conductor. So ITO has 10, aluminum zinc oxide is around 7, so just about as good. But this is for film of aluminum zinc oxide. We're going to make these sprinkled nanometers. Well, just a back of the envelope calculation, you can go through it here. You can make a film with nanoparticles. People have done that. They have pretty high mobilities. You can dope them, so now you have mobility. You have charge density. You can infer a sheet resistance. And so if you made nanoparticles, you could get to 300 ohm per square. So our idea is, well, let's make nanowires that should beat nanoparticles, because there's fewer boundaries for the charge to have to go through to go from point A to point B. So, you know, if you get something that's like 30 ohm per square, that's solution processed at room temperature, you're actually doing okay. That becomes a pretty interesting number. So how do you make zinc oxide nanowires? Well, the problem is that it's very easy to make zinc oxide nanowires. It's not so easy to dope them, because if you make them in water, you're limited at 100 degrees, and the dopant just doesn't want to get into the zinc oxide at 100 degrees. Temperature is not high enough. Aluminum and gallium form alkyl complexes, and so this doesn't work so well. Adon Yang has developed a synthesis that's based on organic solvents of trialkylamine. The advantage is that there is no water to form alkyl complexes with, and you can go to 300 degrees. And so it's actually a very simple synthesis. An undergraduate put this together in about 2 weeks, and you got pretty good material right away. And so you put the surfactant. What the surfactant does, it increases your aspect ratio. So if you put the surfactant, you actually get nanowires. And then the dopant incorporation rate is actually very high. And how do you dope them? It's very simple. Just dump aluminum salt or a gallium salt in your solution, and you get incorporation rates of the order of 60%. So I put 5% aluminum salt in my solution, I get something like 4% aluminum in the zinc oxide. So extremely high dopant concentration and that you obtain really easily. And then this is all, you end up with something that looks like this, a liquid with white powder, and that's dispersed zinc oxide nanolayers. And just for more characterization, we show that they're crystalline. The dopant goes in the wires. You can see that by scanning Auger spectroscopy. You see the gallium and the zinc overlap. So that tells you that the gallium is in the zinc oxide. And control over shape, you haven't really worked very hard, but you get sort of a diameter of the order of 50 nanometers more often, lengths of the order of a couple of microns. And then these are actually very nice semiconductors. If they're not doped, they turn on and off like an intrinsic semiconductor is supposed to do when you make a FET. If they're doped, they behave like a resistor. So everything works the way it's supposed to work. If you take a single wire, it behaves like a resistor. There's still a weak field effect, and so that allows you to measure mobility. So we know that the mobility is about 20 in a single wire, and once we know the mobility, we know the conductivity, we can get the charge density, so we know like about 10 to the 20th per cubic centimeter. And so this wire has a resistivity in the few milliohm centimeters, which is pretty good. You can drop that by another order of magnitude by vapor deposition, and we're working on that. You can get this to about 10 to the 21st. So that's nice, but it's a single wire. What we want to do, we want to make a mat of these. We want to characterize the properties of the mat. And one thing that you wonder is, once I make the mat, what is actually the charge density average across the mat? What is the carrier mobility average across the mat? And you can't do a whole measurement. If you try to make a transistor, that's not going to work either, because you have all these connections, and that will destroy the physical meaning of the measurement. But we realize that what you can do actually is, if you measure the optical absorption of this film, if you have enough free carriers, then they give rise to Drude absorption in the IR. And the shape of the Drude absorption actually is directly related to the carrier density and their mobility. The only thing you have to assume is the effective mass, which is well known as crystalline zinc oxide. And so we said, well, if we can measure the absorption in the IR of this film, then we're home free. We can measure the electronic properties. The problem, though, is that this film scatters highly, and so you can't really measure absorption, especially you need to measure it very sensitively, because you want to measure this edge that goes down the gap. But that's where our photothermal deflection comes back to help us, because that doesn't measure the light that goes through. It doesn't really care about the light that gets scattered. It only measures the light that gets absorbed. And so we are able to measure the optical absorption sensitively. And so to give you an idea of what you expect, the black line is what you expect, let's say, for a certain mobility and charge density of the carriers in the zinc oxide. So you see this is in the IR. If you increase or decrease the number of carriers, what you do is just shift the curve rigidly up and down. If you change the mobility, on the other hand, you change the shape of the curve. So by just looking at the curve, I can tell whether my mobility is dropping or whether my number of carriers is dropping. And so this is the measurement. So you see we successfully measured this edge in the IR, and we just fit it to the Drude formula. The only subtlety here is that we take a distribution of mobilities and a distribution of charge densities. And so now we have our mobility as a function of percentage aluminum, for example. And so we see, can already tell what changes from here to here is the mobility, because it's a shape of the curve that's changing and not the absorption edge. And so in fact, you have what you expect. As you increase the number of aluminum atoms, the mobility goes down. And unfortunately, the number of charge carriers stays constant. So we put more and more aluminum in, but we don't get more charge carriers. So that's bad news. We have to work on that. The bottom line, though, is, let me go quickly through this, to show you the end result. Now, when we do things right, when you do things right, you actually get films with a sheet resistance of about 1 kilo ohm per square. So that's still too high, but we're not really trying so hard right now. We have just made materials and put them together and spray them and this and that. So I think this is fairly promising. We need to drop another order of magnitude to be somewhat interesting. So right now we're stuck at 1 kilo ohm per square, and the reason why we're stuck is because, as I showed you earlier, we can't get enough free carriers in our zinc oxide. So that's a conductivity, but it turns out there's another interesting thing with zinc oxide. This is a cross-section of an amorphous silicon solar cell, And you all know that the transparent conductor in a cell, you want it to be rough so that it scatters light. Typically, zinc oxide is actually etched in dilute hydrochloric acid to make it rough so that you get nice scattering. And so this is what you do in an amorphous silicon process. So what we found is that by changing the surfactant, we can get wires, little particles, or what my students call berries, which are assemblies of little particles. So that's nice because now we have the opportunity to tune the scattering by changing the shape of our particles. And this is the work that we did with Dietmar Knipp, where he had a calculation that showed that you actually get fairly high gains in JSC. In this case, he calculated an amorphous silicon cell because he wanted to have a very well-controlled system. If you have features on the order of 100, 200 nanometer high. And if you look at the scale bar is 500 nanometers, so we actually have exactly that feature size. We have another very nice thing. We have roughness over 2 length scales. We have roughness over a length scale of a few hundred nanometers. We also have these little particles that are much smaller. It turns out that this may be important in scattering. How do you quantify scattering? It's a haze factor, just very simply. Shine light through the film, and then the haze is the diffuse transmission divided by the total transmission. So we use an integrated sphere to measure that. And remember, we want to do things cheaply, so we developed with Peter Pointerman's a spray cooker. So this is a picture of a spray cooker. This is a spray cooker film. And so we just put the precursor solution, which is a solution of our nanowires and nanoparticles, and it gets sprayed over. Our substrate is actually about 30 by 30 centimeters. So we can do this very quickly. And so this is the interesting result. Now the blue curve is sort of state-of-the-art scattering zinc oxide, which is done by LPCVD by controlling the CVD conditions. And this was published recently, and I was told this is absolutely state-of-the-art. And so this is a transmission, blue here, and this is a diffuse transmission. And now if you look at our spray-coated nanowires, the transmission is very comparable, but the diffuse transmission is actually higher in the IR, which is where you want it. That's where you want the scattering for light tracking. The particles are actually even better. You see the transmission in black is comparable to the LPCVD. The diffuse transmission is actually much higher, all the way from 600 nanometers to 1.1 microns. So we get layers that scatter very, very nicely, better than state-of-the-art LPCVDs and oxide. These are just sprayed on the surface. It takes about 10 seconds to do that. So the haze factor that we measure is extremely high. As you increase the number of passes, you get a higher haze factor. You can get up to 70% of the light being transmitted as diffuse light and not direct light. So this is an extremely high haze factor. I'll skip on this. So last thing very quickly, sorry Gary. How do we incorporate, have we started incorporating this in solar cells? We have. Eventually we want to go to ITO free, but right now we just want to test whether the material works at all. So this is the geometry, ITO, then we have our zinc oxide that's embedded in the PDOT or not, and then a multijunction solar cell on top of it. First attempt, not too bad. This is the original cell in red. If you have PDOT-coated zinc oxide nanowires, the short circuit current goes up. The efficiency doesn't go up because the fill factor took a hit because we can't make cells as good as we can on ITO PDOT when you have these rough nanowires. But it's still encouraging because the short circuit current goes up. Further attempt was a little bit better. So I just want to focus on this one. Thin zinc oxide, bare zinc oxide nanowires. It's the green curve here. And you see that the efficiency is slightly higher. I'd say that's probably within the error. But the interesting thing is that the EQE is actually higher at longer wavelengths. And the reason why the efficiency is just about the same is because we take a hit at shorter wavelengths. But the fact that the EQE is higher at longer wavelengths, I think, is encouraging in this approach. May allow you to get a bump up in efficiency very simply and very cheap. You're just spraying these nanowires on the solar cell. So these are my conclusions. I'll leave them here because I think I've gone actually just in time. So thank you for your attention.
Thanks very much, Alberto. We have time for some questions.
The thermodynamic driving force controls the brakes. The difference between the driving force and the reorganization energy controls the brakes. So the two have to be the same. So you always want to have some differential gaps that equal the reorganization energy. So, but when you change your
smooth looking.
Yeah, you've got me going on the CT stage. First, you showed that you think that the homogeneous they have a rather broad dispersion at the interface because they have all these different interactions, right? And then Jean-Luc comes with two preferred CT states. If there are many possibilities there, but one of the things would be that only certain configurations lead to a CT state, and that another percentage of the interface is without
dead, yeah.
right? If that's one option. Is that the one that is that your picture? Or is the picture that there are way more CT states with slightly different configurations?
Well, I think if there were a lot of different CT states, we wouldn't see these two halves that are
That's the problem.
fairly well resolved.
Yeah. So it sounds like there's a few orientations that lead to CT states. And this gives me a completely different vision on how the interface is, because the interface might be heterogeneous. Certain parts do have CT and certain parts don't.
I think that's...
Which makes it even more interesting.
Yeah, I think that's a very possible. So, like I said, my background is in transport, where you imagine things having all possible configurations, and I could never understand why you don't think the same way about these interfaces. And so what you just said is sort of what I think too, is that the interface, these things phase separate fairly quickly, but definitely in a pretty messy way. And so, yeah, then you anneal them to do different things, but the mobility of the phone at that point is not so high. And so I absolutely agree. Maybe part of that donor acceptor interface is just dead.
And that could also explain in part the difference between usually polymer and polymer.
The symmetry of the fullerene, I think, plays a role.
It's much easier. Yeah, the fullerene is around.
Exactly. I agree. I think that's one of the aspects of fullerene that's a little magical. That's exactly that. Is the spherical symmetry. No matter how you look at it, it always looks the same.
I have a simple question concerning the charge sample state. Have you tried to take a look at what happens to the charge sample state when you apply the external electric field? So for example, there's some change in the absorption.
No, so we haven't, in this experiment, it's difficult to do that. We'd like to do it, but it's not so easy, because if you remember, let me show you what the setup looks like. The film is immersed in a liquid. So, I mean, it's doable. You have to put electrodes. The other thing is that the film has to be exposed to the liquid. So either you make a very, very thin electrode that doesn't perturb the heat flow into the liquid, or you can only do it laterally, and then laterally you're not going to be able to put very large electric fields. There is another variation of this measurement, where rather than measuring the heat that comes out, you measure the photocurrent. Essentially, it's called a constant photocurrent method. So in that case, it's easier to put an electric field. You put a bias, then you chop a small signal, and you might be able to measure that. So yeah, that would be an interesting experiment to try.
One last question.
On the second part of the talk, when you talked about making the doped thin films, and then you got a particular sheet resistance. What was the value of that sheet resistance again?
So the best we got is just under a kilo ohm per square.
1 kilo per square.
Per square.
Right, okay. Because when you take very dirty metallic thin films, when you make them dirty enough or thin enough, eventually they undergo a metal insulator transition. And there's some characteristic resistance that's sort of universal associated with that. I don't know if there's, which is of the order of kilos per square.
These are not doped enough to be thought about as being truly metallic, and they're porous. They're pretty messy. So the kilo ohm per square, we're fairly convinced, is due to the wire-to-wire contact resistance.